morning to everyone. My name is Zouhayr Arbib. I work in FCC Aqualia. And well, I came here today to present the Allgas project, where we want to transform the urban wastewater or industrial wastewater into valuable algae biomass for biofuel purposes. The European Commission is participating in the funding of three large industrial projects where the aim is the production of biofuels throughout the use of microalgae biomass. The three projects, Biofat, Allgas, and Insusal, shares the three main objectives which were clearly indicated in the FP7 call. The first one is the design and construction of a cultivation area at demo scale, 10 hectares of cultivation area, to reach an annual productivity of 90 tons per hectare per year, and it was avoided to use any kind of CO2 from fossil fuel origin. In the case of the Allgas project, we have also some specific targets different to the other two projects. The first one, and the most important, is the use of a low-cost or even non-expensive culture medium. We are interested in recycling the nitrogen, phosphorus, and carbon contained in the wastewater. And the most important aspect to highlight here is the phosphorus, because the reserves of phosphorus in the world are limited, so we can use it for cultivating biomass for biofuels. So it's a critical point. The other objective of the Allgas project is to use a low-cost, robust, and very simple photobioreactors. It's the only way to get in good numbers for producing biofuels. In our flow diagram, we want to combine the algae cultivation with anaerobic digestion, and if it's possible, the biodiesel production from the fresh biomass or anaerobic digested biomass. And finally, we want to design a sustainable process from the technical and eco-friendly point of view. The Allgas project is composed by 6 partners. From Spain, FCC Aqualia is the coordinator of the project and the work package leader of cultivation, harvesting, anaerobic digestion at big scale, and also the responsible of the design and construction of the final demo scale, 10 hectares. From the UK, the University of Southampton is the responsible of developing of all the lab scale anaerobic digester experiments. Hygear is the responsible of the upgrading of the biogas produced in the anaerobic process. They must produce biogas with the specification to feed the fleet vehicles that will be provided by Volkswagen. BDI is in charge of the extraction, characterization, and production of biodiesel from the algae biomass that we produce in our plant. And finally, Fraunhofer is in charge of the life cycle analysis of our process. Before starting a project of cultivation of algae, we must solve some critical questions. The first one, where to locate our project. We want to cultivate microalgae. Microalgae are photosynthetic microorganisms that needs carbon, nitrogen, and phosphorus, but especially solar radiation, light, and a proper climatic conditions. This is a typical radiation map of Europe. The red color indicates the zones where the radiation is higher. So in the Allgas project, as a European project, we decided to implement the project in Spain, and more specifically in the South Spain, in the province of Cádiz, where the radiation is very high. It's suitable for growing algae, but also the temperature is appropriate. The average is 80 Celsius degree during the whole year, and the rain during the whole year is lower than 500 millimeters. The other question to solve is the water. We don't want to compete with traditional agriculture for human feed, and also we don't want to use fresh water, and we don't want to use seawater, because the capital cost when you work with seawater is very high. So the numbers are very simple. So we decided to implement our project of algae cultivation near wastewater treatment plant, where we have a huge amount of wastewater. In this case, we selected the wastewater treatment plant of Chiclana de la Frontera in Cádiz, where we have an average flow of 10,000 cubic meters per day to use for growing algae. And the third question is the land. As in the other case, depending on the technology selected, open system or closed system, cultivation of algae requires a high amount of surface, especially the open systems. So we must select a non-arable land for not competing again with the human needs. We selected Chiclana de la Frontera because we have hundreds of hectares of abandoned salines ready for using and growing algae. Another interesting question to solve is what kind of photobioreactor. I think Dorinde showed us a great presentation about the comparison of technologies. But according to our experience, well, there is a long-term discussion between the advantages and disadvantages of open and closed systems. But this comparison must be made always considering your final objective of the biomass. In our case, for deciding what kind of photobioreactor to decide, it was very easy indeed. We analyzed the capital cost, the operation cost, and the net energy ratio. For biofuels, you must do this deep analysis of what kind of photobioreactor to be used at the end to implement. Of course, in our case, we decided not to use closed system because the capital cost is very high, and according to our calculation, the net energy ratio is lower than 1, so we are not interested in it. We are putting more energy in the system than energy that we can get from the biomass. So finally, we decided to implement in our project, in the Allgas project, the open system, the conventional raised ponds or high-rate algal ponds. This system has advantages. They are simple and robust, low capex and opex. Low capex if the land is for free, of course. It's suitable for using wastewater as culture medium. The open system can have a lot of problems of fouling. And also, the net energy ratio is higher than 1. And of course, the well-known disadvantages of this kind of system is the contamination. But we work with wastewater. We don't care about contamination. The low control of the process. Our objective is to have a very simple process. So we don't want to control every parameter of the raceways or the downstream of the process. And of course, the low productivity in comparison to the closed systems. Summarizing a little bit, the big questions to solve, the first of all, is select properly the location where to implement your project. Light and temperature is very important. No drinking water, no arable land. We don't want to compete with agricultural activities. We must use robust system, simple and low-cost photobioreactors. And finally, in our case, we want to work with open systems and wastewater. So we cannot try to work with pure systems. We can find 1,000 or hundreds of papers and book chapters in literature where you can find references of super species that can accumulate 80% of lipids. But in the reality, you can't achieve this kind of numbers in long-term operation of photobioreactors. So in open systems and wastewater, we have to deal with the natural bloom, a spontaneous growth of algae, different species of algae. Normally, you have a variation during the whole year, dominance of different species, so we have to deal with this kind of cultures. How to implement the final demo, how to get the know-how of to design correctly the final demo scale. It's 10 hectares of cultivation area, it's very big. So in our opinion, the scale up of the process to understand how it works is absolutely necessary. In FCC Aqualia, we started working in the field of algae in 2010 with basic research, lab scale, controlled condition, and flask, controlling all the parameters for understanding the process, getting the kinetic parameters for nutrient removal, biomass production, oxygen production. In 2011, we started the operation of our pilot plant, total cultivation area of 200 square meters. Since September 2014, we upscaled the process to 1,000 square meters, to raise with ponds of 500 square meters each one. And we wish to start the construction of the first part of the demo, which will comprise 3.6 hectares in September, next month, in 2 or 3 weeks. We're going to start the construction of the demo plant. And well, in 2016, we wish to finish the final 10 hectares cultivation area, which was the objective, the main objective of the FP7 call. The Allgas process is based in the interaction between microalgae and bacteria. When we have these two microorganisms together in a culture medium, they work symbiotically. That means that the microalgae uses the sunlight and the nutrient contained in the wastewater, mainly carbon, nitrogen, and phosphorus, to grow, to multiply, and to produce oxygen. This oxygen is used by the aerobic bacteria to degrade the organic matter, the CO2, and to transform it into the COD, and to transform it to CO2 and water. This CO2 is again used to satisfy the microalgae inorganic carbon demand. So we produce biomass for biomethane or biodiesel, a reusable wastewater. We have an economical benefit by treating the wastewater, which is an added value of our system. And also we have a biomass with great biofertilizers capacity. This is the first approach of the Allgas project. The second approach is based that we know that the wastewater is high energy content, almost around 4 kilowatts hour per kilogram of COD contained in the wastewater. So the second approach is based in the pretreatment of this wastewater by a USB reactor, an upflow anaerobic sludge blanket, where we transform part of the organic matter contained in the wastewater into biomethane. The average yield of biomethane of this system, operating at ambient temperature, is 200 liters of biomethane per kilogram of COD. And the rest of the nutrients, the nitrogen and phosphorus, remains constant. So we send it to the algae ponds. Now I will show you one of the final diagrams of the Allgas project. As I said, we pretreat the wastewater in USB reactors, big-scale USB reactors. We produce biomethane, a biogas, which is composed by biomethane and CO2, and a pretreated effluent, which we send to the cultivation area. In the cultivation area, we remove the nitrogen, phosphorus, and carbon, and we produce biomass. Then we harvest, we pre-concentrate the biomass in a harvesting skid. And here we have two alternatives of managing the biomass produced. And the alternative one, which is the most attractive for us, we digest directly the biomass obtained after pre-concentrating. We reach 3–4% of total suspended solids. We digest it, we produce a biogas. The CO2 produced in both anaerobic processes, the USB and the anaerobic digester of the biomass, will be used to satisfy the inorganic carbon demand of the ponds, together with the CO2 produced by the bacteria. The biomethane produced in both anaerobic processes will be mixed, upgraded, and used to feed and sent to a gas station to feed the Volkswagen cars. The residual biomass of the anaerobic digester will be dewatered in a centrifuge. We don't care here about the energy because the flow is very small, because in the previous pre-concentration step, we concentrated at least 100 times the volume. Then we solar dry the dewatered biomass. We mix part of this biomass with green waste. We can use any kind of fossil fuel CO2 to feed a biomass boiler. And this biomass boiler, we obtain an exhaust gas, which contains CO2. So in case of needed, we use this CO2 to add additional inorganic carbon to the algae ponds. And the excess of heat is used to maintain the anaerobic digesters at optimum temperature, 35 or 55 Celsius degree. The second alternative, which is less interesting for us, but we are trying to get good results, is to directly the pre-concentrated biomass, solar drying, oil extraction. We produce biodiesel, and the residual biomass of this step is used to feed the anaerobic digester. As I said, this alternative is less interesting for us because we have two-step dewatering and two-step drying system, so it's not interesting. But we must try to analyze this option. So this is an aerial view of our plant in Chiclana de la Frontera, the pilot plant inside the wastewater treatment plant, And in an exit area, we have the prototype plant, 1,000 square meters. The pilot plant is composed by a complete pretreatment of the wastewater, composed by 3 20 cubic meter USB reactors, and a complete downstream upgrading of the biogas, composed by sulfate treat, sulfide removal, methane stripping, and gas holders. And the cultivation area of the pilot plant is composed by 6 3 square meters, those one, and 6 32 square meters, those one, hybrid algal ponds, and a complete harvesting skid where we try to harvest the biomass throughout sedimentation, filtration, and dissolved air flotation. And the best option that better works was the dissolved air flotation process. The prototype plant, regarding the cultivation area, it's composed by 2,500 square meters reactors. The left one is based in the typical raised waste pond, where the liquid is circulated by a conventional paddle wheel. And the right one is a new innovative low energy algae reactor, where we made a deep modification of the bends, and we changed the paddle wheel by a flow buster with a submersible mixer. What we got with this modification was a drastic reduction of the energy consumption in the step of cultivation, which was very high. Operating at 25 centimeters per second of liquid velocity, we passed from 0.6 in the paddle wheel to 0.1 watt per square meter installed in our installation. Regarding the downstream of the prototype plant, well, it's composed by pre-concentration based in a dissolved air flotation process with a treatment capacity of 20 cubic meters per hour. In this step, our minimum concentration factor is 100, and we can reach even 150 and 160. Then this pre-concentrated biomass is sent to the anaerobic digesters. We have 3, 2 of 600 liters and 1 of 1,500 liters, operating in mesophilic or thermophilic range of operation. As I said previously, the residual biomass is centrifugated in a decanter centrifuge, largely used in wastewater treatment processes. The water biomass is sent to a greenhouse solar dryer provided by Huber, a German company. This solar dryer is enhanced by air solar captors, so we reduce the solid retention time inside the greenhouse to reach a final concentration of solids of 95%, 5% of water. And well, the dried biomass is part of this biomass mixed with green waste is burned in a 25 kilowatts biomass boiler. So part of the CO2 we send it to the ponds, and the excess of heat we send it to the anaerobic digesters. This is the pilot and prototype, and well, this is the view of the space that we have available for scaling up the process. It's near the wastewater treatment plant, and we have more than 100 hectares available for upscaling our process. The demo one, the first stage of the final 10 hectares, will be composed by 7 raceways of 5,200 square meters each one. We will install also 2 units of dissolved air flotation systems with a total treatment capacity of 220 cubic meters per hour, 2,000 cubic meter anaerobic digester, 200 kilowatts biomass boiler, a complete biogas upgrading plant, a gas station, and a Volkswagen car for testing the gas obtained in our plant. Well, some interesting results. Those here present the results obtained during the last 12 months of operation of the prototype plant regarding the wastewater treatment capability and the biomass production. Well, as we can see, we are treating in this 1,000 square meters around 100 cubic meter of water per day. This is an HRT of 3 days average. Now in summer, we are operating below 2 days, which is a very high dilution rate. 2 minutes? Oh, 2 minutes. Vale. Well, we can remove almost 75% of the total nitrogen and 85% of the total phosphorus contained on the water. And as you can see here, we generate an effluent that fits the most restrictive limits of the European directive. And regarding the biomass productivity, well, we are between 75 and 110 tons of total suspended solids per hectare per year. We are near to the target of the FP7 call, which was 90 tons per hectare per year. Regarding the bioenergy capability of our process, we operated 3 anaerobic digesters at mesophilic and thermophilic range of operation, and well, the results obtained were similar to those obtained in the conventional wastewater treatment plant. But we have to note that the biomass produced in this process, in the Allgas process, is 3 or 4 times higher than in the conventional wastewater treatment plant. Therefore, the production of the energy production capacity of our process is very high. But we know that we can increase even this biomethane yield. Now we are working in pretreatment of the biomass with the aim of the cell disruption, the cell wall of the algae. We are testing different techniques, ozonization, thermal, enzymatic, and chemical. This is just an example of some BMPs, biomethane potential experiment, obtained with raw wastewater and thermal pretreated wastewater, 170 Celsius degree and 6 bar of pressure. And as we can see here, we can get 2 times we can increase 2 times the biogas yield of our process. And finally, by using all the data obtained in the prototype plant during 1 year of operation, we made a balance where we compare a conventional wastewater treatment plant at your left and the Allgas process. 10 hectares, the final 10 hectares of cultivation, or 10,000 cubic meters of wastewater treated. Regarding the electrical consumption, well, with the new concept of the Allgas project, we can reduce more than half the energy consumption required for treating the wastewater. And on the other hand, the energy produced in the conventional wastewater is lower than 50% of the energy demand of the plant. And in the case of the Allgas project, we can produce more than 2 times the energy that we need for operating the plant. So we have an excess of energy of our plant. We have a self-sufficiency of near 250%. If we focus on the Allgas project, this excess of energy, after satisfying the demands of our plant, is equivalent more or less to 1,600 kilograms per day of algae, which is more or less 260 kilos of biomethane per day, after satisfying all the electrical demand of our plant. Doing a quick numbers, if we consider that a biogas car consumes 5 kilo of biomethane every 100 kilometers, with this excess of biomass in our plant, we can run 100 cars, or we can travel around the world 4 times. Our next objective is in next month to start feeding the first car with the biogas produced in our 1,000 square meters prototype plant. Thank you so much.